Now, one final thing to consider is how we can use that previous theorem for estimating the error, or the remainder, to approximate the sum of the series. So we had previously that Rn was somewhere between the integral from n to infinity on the upper end and the integral from n plus 1 to infinity on the lower end. And in fact here Rn, we said earlier, was the difference between the sum of the series and the partial sum Sn. So I can isolate the sum of the series in the middle by adding Sn to either end here. So it's like I'm adding Sn here, adding Sn here, adding Sn here. Okay, and that's how we get this result here. So this will tell us that the actual sum of the series, S, right, S would be the actual sum of the series, will be bounded somewhere in between that partial sum, Sn, plus the integral from n to infinity on the upper end, and Sn plus the integral from n plus 1 to infinity on the lower end. So for instance, in the previous example, we were looking at the series 1 over n cubed. So what would be the upper and lower bounds for this series? Well, we computed S10. And we also computed the integrals that would give us the error bound. So we computed from n to infinity would be from 10 to infinity here. And then on the lower end, it was from 11 to infinity. Okay, so if we put the pieces together that we had in the previous slide, we can get an upper and lower bound on the actual sum of the series. So let's do that now. So using the values that we had from the previous slide for S10 and for this integral, that gives us here a lower bound of something around 1.20166, and then an upper bound taking the partial sum S10 plus this upper bound, which was 0.005. We have 1.20253 roughly. So that gives us a good tight interval on which we can get the actual sum here. So we know our actual sum is going to lie somewhere in between these values.